Dun, 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 we're finally here, the Stoichiometry podcast. I'm excited. I know you're excited because it means it's the last one. Before we go into stoichiometry, which is really just a fancy way of saying counting, I want you to remember and think back to the mole map that we went over in the mole um, podcast, where if you have the number of moles and you want to get to anywhere else, you're going to multiply going with the arrow. So go from moles to grams, we're going to multiply by the molar mass, multiply by Avogadro's number to get to particles, and multiply by 22.4 to get to liters at STP, and we do our dance. To go back from any one of these three back to mole, we divide going against the arrow. So divide by 22.4, Avogadro's number, the molar mass. I want to add one final one in here, and that's molarity. If you're given the concentration of a solution, or the concentration of ions, it's symbolized by a capital M, which stands for molarity, which is moles per liter. So since it's moles per liter, our arrow, instead of going away from moles, is actually going to go towards it, like this. Where on this line would be the volume. If it's in liters, great. If it's in milliliters, then realize we'll end up with millimoles, a unit we'll get into more later, but millimoles is just, 1/1000th of a mole. Molarity is often symbolized by these brackets around whatever it is we're talking about. So if I'm talking about the concentration of chlorine ions, I could symbolize it or shorthand it by doing brackets, Cl minus, and then close bracket. All right, so remember your table or your chart, graph, whatever we're calling this, figure. Moving on. There are two ways you can do stoichiometry. Well, actually, there's an infinite number of ways you can do stoichiometry. However, I know of two, and I'm going to try to teach you two in under the 15 minutes that this video has to be. All of them start in the exact same place. You absolutely must have a balanced chemical reaction before you can do anything with stoichiometry. So, here's a problem. What is the mass of oxygen that will react with 96.1 grams of propane? So, again, this is all words. We have to turn this into a chemical equation. And it's going to look something like this. So that's our unbalanced equation. Propane, pro being the prefix for 3 carbons, and then I just have to balance out the number of hydrogens. If you didn't know what propane was, don't worry, we will use it so much you will know it by heart by the end of the year. Plus oxygen, this is a standard combustion reaction producing carbon dioxide and water. Once you balance it, it's going to look like this. 5 oxygens plus 1 propane gives us 3 moles of carbon dioxide plus 4 moles of water. Realize that these coefficients can be said as moles, molecules, well, moles or molecules. So, now, there are two ways to do this. I'm going to run through the dimensional analysis first, and then I'll show you the table. If one works for you better than the other, that's great. I do not care which one you use, as long as I can follow along. Well, actually, as long as your grader can follow along. Screw me. Focus on your grader. Alright, dimensional analysis. Remember, for dimensional analysis, you always start with what you're given, so grams of propane, and then you're going to do an arrow for what you're trying to get to. So I'm trying to get to grams of oxygen. Now there's got to be some steps in there, so when in doubt, we don't use grams, we're going to go from grams, we're going to go to moles, and not only moles, but it's got to be moles of what we're given. So we're given propane, so grams of propane to moles of propane. Once again, we can't complete this step, we can't go from moles of propane and just outright change the compound we're talking about. So we need to change the compound we're talking about so we can convert from moles to moles. From moles of propane to moles of oxygen using the mole to mole ratio of one compound to another. So the mole to mole ratio here of 5 oxygens to 1 propane. And then from oxygen, we can go from moles of oxygen, we can go to grams of oxygen, which will close this out. Whatever came before the arrow goes below. So let's fill. So whatever came before the arrow goes below, grams, grams, moles, 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 and we end with grams. Again, we can double check, make sure our units cancel out. Grams above, cancel grams below, moles above, cancels moles below. Moles above cancels moles below. We're left with just grams of oxygen. We should mathematically be, or at least by units, be able to work this out. Now let's fill in what we're given. We were given grams of methane, so let's put that. 96.1 grams of methane. The mole is always bigger, so let's put a 1 in front of the mole. And then we need to find the molar mass of methane, so we look at the periodic table and we find that it's 44.11 grams per mole. And then again, we need to convert from moles of methane to moles of oxygen, so we're going to use the mole to mole ratio. So let's plug that in. It's 5 to 1. Remember, that's just the coefficients in front of the reaction from the balanced chemical reaction. Lastly, we have moles over grams. Moles always bigger. In oxygen, there's 16 times 2, so 32 grams of oxygen for every 1 mole. If we multiply everything across the top and divide by everything on the bottom, we'll figure out how many grams of oxygen we need, which we come out to find is 349 grams. Again, make it big, circle it, put a square around it, star it, so that your grader can give you all the points you deserve for doing all that hard work. Again, if you're a step person, you can just do this, and then do this step, and then do this step, and then end up with the same answer. It doesn't matter to me as long as I can follow along with your work. Alright, dimensional analysis, factor label method, same way you learned in Gen Chem. However, the NIMSY people have given me a new method, so I'm going to show you that now, and that's this table method. And I have to give them some credit. The table method does make sense because we are going to use a lot of tables, and we're going to do things use a lot of tables in the months to come ahead, especially when it comes to equilibrium. And the way that this table works is that you take the balanced chemical equation and you drop it into right here where it says balanced chemical equation. Step number 1, done. Make sure you have a balanced chemical equation. Next, you fill in the molar masses for each element, or for each compound, each element in the reaction. So I'm going to do that really fast. So now as you got your molar masses plugged in, you move down here to where it says mole to mole. This is where you put your mole to mole ratio of one element to another. And you have to understand that in front of every compound, there is an understood 1 unless there's a different coefficient. So the mole to mole ratio here is 1, 5, 3, 4. Next, they want you to skip a step and come down and put in amount. This is where you put your gram amounts, volume amounts, particle amounts for whatever it is you were given, and this is also where you're going to put whatever it is you're looking for. So I'm going to put in, I was given 96.1 grams of propane, putting that right meow. Alright, now we're ready to start. How many moles, we have to fill in with this table above, how many moles of propane is that? So remember, we're going to take this number and divide by its molar mass to come out with how many moles of propane we have. So when we do that, we find that we have 96.1 divided by 44.1 comes out to 2.179. Therefore, we have 2.719 moles of propane. Now you take that, if 1 is 2.79, what would 5 be? And you simply fill that in here. So 2.179 times 5 comes out to be 10.893 moles of oxygen. We're still not done. They were asking for it a mass, so it has to be in grams. So we're going to take this value and multiply by the molar mass to end up with our final mass of oxygen, 349. Table method, dimensional analysis, same answer, two different ways to go about it. No matter which way you use, it'll be rare that you're given just the mass or volume or number of particles of just one reactant in a multi-reactant problem. It's more likely you'll be given two reactants. Or in rare case that the AP test is feeling exceptionally hard, they'll give you all of the reactants. And this is a case where you have what's called a limiting reactant, something that limits how much you can make. And I like to fall back on my grilled cheese example. If I'm making grilled cheese and I have 2 pieces of bread, 1 piece of cheese, that's going to make 1 whole grilled cheese sandwich. But if I had 40 pieces of bread, but still only 1 piece of cheese, I can only make 1 grilled cheese. That would be a limiting reactant. The cheese is limiting how much bread I'm using to produce how much grilled cheese. Let's do one of these so you can see how I recommend you do it. If you come across another method, by all means, as long as I can follow your logic, you'll get the points. Here we have a limiting reactant problem in which we are given the mass of 2 reactants, and we need to determine which is the limiting reactant, and then based on that, because we can only produce as much as our limiting reactant will allow us, we need to figure out how much nitrogen is produced or how much product is produced. So once again, we have to always start with a balanced chemical reaction. Our balanced chemical reaction is 2 ammoniums plus 3 copper oxides gives us 2 nitrogens plus 3 coppers plus 3 hydrogens. Now, I start by putting the 2 reactants I'm given on 2 separate lines underneath of where they are in the reaction. Let's do that now. Alright, so now I can visualize. I see 18 grams of this, 90 grams of that, producing how much of this? This is what I'm ending up looking for. Alright, but grams don't do us any good. As I said, you should always take grams, and pretty much on rare occasion, but almost always, you need to convert these to mole. So let's convert these grams to moles. So I'm going to divide both of these grams by their molar masses, and when I do that, I end up with these values. 1.064 moles of ammonium and 1.136 moles of copper oxide. Again, I'm going to leave these conversions here so you can see where they came from. If you don't believe me, you can do the dimensional analysis. Comes out right. I like to live in a perfect scenario type of world. So I'm going to pretend I have an infinite supply of copper oxide to start with. And I'm going to ask how many moles of nitrogen gas would I produce? And then that, well, we'll just see in a second. So if I had an infinite supply of copper oxide, how many moles of nitrogen gas could I produce? Well, we're going to use the mole to mole ratio. So it's going to be 1.06 divided by 2 times 1, which comes out to be 0.5320. Conversions up here if you're following along. I'll do the same thing down here. If I had an infinite number of ammonium, how much nitrogen can I produce? Well, we're going to go through the mole to mole ratio. 1.1 divided by 3 times 1. Come out with our moles of nitrogen, which is 0.3787. Again, conversions down here. Now the question becomes, which is our limiting reagent? Well, our limiting reagent is going to limit how much we produce. So whichever scenario produces the least amount of moles is our limiting reagent. So in this case, 0.3 is smaller than 0.5, so our limiting reagent is the copper oxide scenario. Circle it and make sure the reader knows that that's what we know to be our limiting reagent. Now our answer must be based on this. Well, look, we've already calculated moles of nitrogen, so we're just going to take this number, multiply by the molar mass of nitrogen, and we'll have our answer, which we find 10.6 grams of nitrogen. Circle it, make it big, and we get our points.